and we see this ringing of activity in layer 4, which even is still preserved when the stimulus has already ended. So this negative target specificity also helps in having a crisp pulse in the system. So if we summarize this result in a cartoon, then the picture would be like this: that in blue, excitation is propagating in the system, and whenever the activity has reached one station, then there's a mechanism that stops the activity in the layer where it came from. And so what we want to do in the next step is to try to reconstruct a local field potential from this scenario to better compare it to experimental data. Now, this slide summarizes a bit of critique on this approach. Now, this is the system we have worked with, but what one should realize is that we can represent all the local synapses essentially, but still 50% of the synapses of this system coming from outside. So it's clear that this severely restricts the predictive power of such a system, because we don't know what to do with these inputs, which are making 50% of the total ones. We can either only replace them by a DC current or by random noise. There's nothing more we can do. This situation becomes a bit better if we are studying larger systems like areas, where then more of the connections are represented. But ultimately, if we want to close the functional loop, to have a system that is really doing something, we have to go to the brain scale, because most of brain function is distributed over many areas in the brain. So to summarize, in the first part, I have discussed the consistency of layer-specific connectivity data in a comparison which is based on connection probabilities. And although it initially seemed that two different sources of experimental data give different results, we could explain them by methodological differences and integrate them into one data set. And using this data set, then we could show that in this multi-layered structure there is a low-rate asynchronous irregular state. And I have not discussed in details, but if you set up this system, you notice that it's very easy to stabilize this, so you don't have to fine-tune. And in the study, it turned out that the target specificity is an important parameter to stabilize the system. So the next step for us is that we now want to construct also a local field potential in this structure, and as you said, study correlation and synchrony. Yes.
One question. These results are robust to other neuron models?
Yeah. Yes.
Even resonator models?
Yes. Yes. And there's you can also put in short-term plasticity, and you find that this is not influencing the stability of the system. So it's not the critical factor.
And the computational time is mostly due to the conductivity computation, or the integration of the dynamics is pretty high also. The synapses are the component in the system which is dominating everything, right? So you have 10 to the power of 9 synapses in this system. So computation time and memory is dominated by the synapses, which, by the way, also means that instead of using point neurons here, you could also use neurons with a few compartments. It will not dramatically change your computation time because the synapses are the dominating factor.
Yeah, you said that all the excitatory neurons were pretty much the same, so they all have a basically low rate. Did you try with enhancing?
No, this is not what I said. What I meant is that the dynamics of the excitatory neurons is identical. So they have the same membrane time constant and the same threshold and so on. But placing them into this network, their properties are then defined by the position where they are. So a layer 2-3 neuron then behaves differently from a layer 4 neuron. It has a different spike rate, but not because of its own properties.
But all layer 2-3 cells will have a comparable time rate, and all layer 4 cells will have a comparable
no. This also goes back to what Karl explained so nicely this morning, that these neurons have different number of synapses, and therefore they can have vastly different spike rates. It's only the average that is then so clearly distinguishable. Yeah.
And the other question is that you show that if you put there some thalamic input, you will have some variability with each realization.
Yes.
So where that kind of variability come from? It's not the input, it's fairly regular every realization. What is the source of that?
Okay, maybe there is variability, but I'm afraid that there is a misunderstanding anyway. So what you see here are not different trials, but the recording of a bunch of neurons simultaneously. Yeah. But still you are right. If I would repeat the experiment, I would also see this variability. Yes.
What is the source of variability?
Yeah. In this case, the source is that when your pulse arrives, every time the network is in a different state, because it has this highly irregular internal dynamics.
Which contrasts with the experiments done with full image frames that show that every time you get a very precise response. So is that pulse through the entire network or in a particular point?
I think if you want to discuss this, no, it's only to a fraction of the neurons.
Okay.
It's only to a fraction of the neurons.
That's why you have noise.
Yeah.
If you do it, if you have different input, a different portion of the network, I would bet that you have a very, very precise response.
Yeah, but also, I mean, in principle, I think you're right, but also consider the time scale here. So this is only a few milliseconds. So it's
okay.
In this network, you have recurrent relations between neurons.
yes.
How is the update? Is it synchronous and the update of the state of the neurons?
In the simulation. Okay, so I will talk about this in detail tomorrow. I will show you exactly what we are doing. Here the simulation is performed on an 0.1 milliseconds time scale and synchronous. Yeah, so that the spikes are confined to a time grid.
You frozen the state, you update all the neurons, and so on.
Yes.
A question, you said you can lose some synapses, but my question is, you can selection of some synapses with the activity with the input. I mean, the synapses that involve active with the stimulus from the thalamus and the synapses established and the other goes. Is possible with this model?
I think I don't understand exactly what
if the more active synapses is stabilized on time with input from thalamus. I mean, in that figure you